Something is amiss in our cognizance of the universe. Cosmology is moving toward a basic crossroads, wrestling with perhaps one of its most fundamental issues. How rapidly is the universe expanding? For over a decade, two different measurement methods have been at odds. Observations of the present-day universe typically show that the rate of expansion, known as the Hubble constant, is around 9% faster than what is predicted based on data from the early universe. Experts had hoped that the James Webb Space Telescope, the most advanced telescope ever made, would help resolve this issue conclusively. However, consensus has yet to emerge, as the telescope's remarkable, novel observations have further solidified the discrepancy, posing a potential challenge to the established cosmological model. Now, the need for new physics to either modify or entirely replace the 40-year-old theory is under serious debate. An exhilarating and intriguing possibility is that we are overlooking some aspect of the universe. Join us as we delve into how the new ultra-deep images from James Webb have recently confirmed that there is something fundamentally flawed in our understanding of the universe. Our universe began with a bang, the Big Bang. Energy, mass, and space emerged instantly. Shortly thereafter, the young universe formed a growing plasma, a fusion of matter and antimatter particles that arose and annihilated each other as they collided. Left unchecked, the matter and antimatter in this plasma would have obliterated each other entirely. However, scientists believe an unknown asymmetry allowed more matter to form than antimatter, thereby saving the universe from immediate destruction. Gravity then compressed this plasma, heating it so intensely that sound waves, known as baryon acoustic oscillations, traveled through the medium at roughly half the speed of light. Simultaneously, the dense energy content of the early universe stretched spacetime, pushing a small portion of matter safely away from the heat. As the universe expanded like a balloon, the standard narrative suggests that ordinary matter, which interacts with light, began to cluster around invisible dark matter, forming the first galaxies connected by a vast cosmic web. As the universe's objects spread out, its energy density, and thus its rate of expansion, declined. Yet, about 5 billion years ago, galaxies began retreating faster, driven by the mysterious force known as dark energy. The clearest and most widely accepted explanation for dark energy is that it functions as a cosmological constant, a uniform force that remains steady across both space and time, woven into the fabric of expanding spacetime. Named lambda, by Einstein in his theory of general relativity, dark energy density stays constant as the universe grows, while the density of ordinary matter decreases. Eventually, dark energy became the dominant contributor to the universe's expansion. When combined with normal matter and dark matter, the energy densities of these components set an upper limit on the universe's expansion speed. These elements form the core of the lambda-cold dark matter, lambda CDM model, which describes the evolution of the universe and predicts its ultimate fate, a heat death, known as the Big Freeze. Many of this model's predictions have been proven highly accurate. However, this is where the trouble begins. Despite extensive research, astronomers remain unaware of the true nature of dark matter and dark energy. As Afrolov, an astronomy professor at University College London involved in dark energy universe studies, states, most scientists agree that the universe's current makeup is about 5% ordinary atomic matter, 25% cold dark matter, and 70% dark energy. The embarrassing truth is that we still don't understand the latter two. A significantly greater challenge to the lambda CDM model, however, is the growing issue known as the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. The discrepancy is crucial to the point that it has become a pressing issue in cosmology. Measurements made from observing the early universe suggest it is expanding far faster than predicted by the lambda CDM model. These methods have undergone extensive testing and validation through various observations. As Nobel Prize-winning astrophysicist Adam Rees, who led the team responsible for the latest James Webb measurements, put it, measuring the universe's expansion involves more than just using a radar gun. One of the primary methods to assess this rate examines the cosmic microwave background, CMB, the universe's first light, emitted around 380,000 years after the Big Bang. This imprint is visible across the entire sky and has been mapped to infer the Hubble constant with less than 1% uncertainty. Between 2009 and 2013, the European Space Agency's Planck satellite produced a detailed map of the CMB. In this cosmic snapshot, the universe appears nearly uniform, but slight temperature variations, where matter is denser or sparser, mark regions where baryon acoustic oscillations left their imprint. This soap bubble structure expanded into the cosmic web, a network of filaments connecting galaxies at their intersections. By studying these waves, cosmologists deduced the quantities of ordinary matter, dark matter, and the cosmological constant, dark energy, calculating the Hubble constant to be approximately 67 kilometers per second per megaparsec. Let's pause to unpack this number. If a galaxy is 1 megaparsec away, it will recede at a speed of 67 kilometers per second. At a distance of 20 megaparsecs, this recession increases to 1,340 kilometers per second, continuing to grow with distance. If a galaxy is farther than 4,175 megaparsecs, it will retreat faster than the speed of light. Another method to measure this expansion rate involves using standard candles, pulsating stars known as Cepheids. These stars' outer layers expand and contract as they absorb and release radiation, causing them to pulsate in a predictable pattern. This behavior, discovered in 1912 by astronomer Henrietta Swan-Leavitt, allows astronomers to determine the absolute brightness of these stars, which can then be used to measure their distance. This Cepheid-based technique, known as the cosmic distance ladder, was a groundbreaking discovery that allowed cosmologists to measure vast distances. The first rung of the ladder is constructed by measuring nearby Cepheids and cross-checking their distances. From this, the distances of more distant stars and galaxies are determined by observing how much their light has been stretched, redshifted, as the universe expands. By comparing this data, astronomers can calculate the Hubble constant. In 2019, Rees and his team used this method by pointing the Hubble Space Telescope at the Milky Way's nearest neighbor, the Large Magellanic Cloud. Their results were striking, showing a much higher expansion rate of 74 kilometers per second per megaparsec compared to the Planck measurements. However, Planck's results were limited by its lack of precision in crowded regions of space, where distant Cepheids blurred with neighboring stars. Some skeptical astronomers argued that this discrepancy might have been caused by measurement errors. When the James Webb Space Telescope launched in December 2021, it was expected to resolve, or perhaps confirm, this disparity. With its 6.5-meter-wide mirror, more than 3 times the size of Hubble's, and superior infrared capabilities, James Webb could observe fainter objects and detect a broader range of wavelengths. In a study comparing Cepheids in the galaxy NGC 4258 to supernovae, Rees and his team found results nearly identical to their previous work: 73 kilometers per second per megaparsec. Other measurements, including those by Wendy Friedman using the Hubble Space Telescope and gravitational lensing techniques, returned similar results of 69.6 and 66.6 kilometers per second per megaparsec, respectively. Clarifications vary. Some recommend estimation mistakes, others propose new physical science, or a blend of both. Kai accepts that a large part of the data of interest points toward the requirement for new physical science. The main speculation is that dark energy's behavior has changed over time. If dark energy was once stronger and gradually faded, it would cause the universe to appear smaller in its earlier stages, resulting in a faster expansion rate today. Different possibilities include the presence of 2 types of dark energy or dark matter interacting with light. However, these theories present complexities that many cosmologists are reluctant to embrace without further proof. James Webb's discoveries are not just challenging our understanding of dark energy and dark matter, they are reshaping our ideas about universe development. By looking further back in time than ever before, the telescope has uncovered galaxies that were significantly more massive and advanced than the Standard Model had predicted, forming only 300 million years after the Big Bang. Early galaxies, which should have been composed of young, hot stars, were found to contain heavy elements and even very massive black holes at their centers, features that challenge the conventional model of universe evolution. These findings have intensified debates within cosmology, suggesting that the processes governing galaxy formation may have been more rapid and efficient than previously thought. In addition to addressing these significant mysteries, James Webb's findings have further deepened the enigma surrounding dark matter and dark energy. Despite being the dominant components of the universe, both remain poorly understood. While dark matter interacts gravitationally, its exact nature is still unknown, prompting ongoing research into its detection. Similarly, dark energy drives the accelerated expansion of the universe, but disparities, such as the Hubble tension, raise the possibility that dark energy properties are not uniform across spacetime. Alternative theories propose dynamic forms of dark energy that could evolve over time, influencing the expansion rate differently at various stages of the universe's history. To solve these mysteries, astronomers will require both advanced observational instruments, like the James Webb Space Telescope, and theoretical frameworks that can incorporate the new data without discarding the successes of current models. The implications of Webb's revelations extend far beyond cosmology, influencing broader astrophysical inquiries, including the origins of life and the conditions necessary for life to arise on other planets. By studying distant galaxies, astronomers hope to uncover clues about how Earth-like planets might form around other stars, offering potential insights into the prevalence and diversity of life in the universe. Looking forward, the James Webb Space Telescope promises to keep pushing the boundaries of our cosmic understanding. Its unparalleled sensitivity and resolution will enable astronomers to study the atmospheres of exoplanets, map galaxies more precisely, and examine the earliest epochs of cosmic history with unmatched precision. These efforts will not only deepen our understanding of the universe's past, but also pave the way for groundbreaking discoveries that could revolutionize our perception of physics, astronomy, and our place in the cosmos. As Webb enters its operational stage, astronomers eagerly anticipate the new insights that will emerge. Whether unraveling the mysteries of dark matter and dark energy, understanding galaxy formation, or searching for life beyond Earth, the telescope stands at the forefront, poised to transform our view of the universe in unimaginable ways. In conclusion, the intersection of cutting-edge technology, theoretical innovation, and precise observation heralds an exciting new era for cosmology and astronomy. James Webb's contributions are set to play a pivotal role in refining our understanding of the universe's origins and evolution, challenging established theories while simultaneously opening doors to groundbreaking discoveries. As we venture further into this exploration, the mysteries of the universe await, with the James Webb Space Telescope leading the way in uncovering the secrets of our cosmic legacy and future. The impact of the James Webb Space Telescope, JWST, goes beyond measuring the expansion of the universe or revealing the details of early galaxies. It is also poised to address some of the most profound questions of cosmology. That our current understanding of the universe might be flawed is not a new idea, but the precision of JWST's observations has brought this possibility into sharp focus. This includes understanding the behavior of dark matter and dark energy, which are key to the universe's large-scale structure but remain elusive. One of the most exciting aspects of JWST lies in its ability to study the early universe in ways that previous telescopes, such as Hubble, could not. With its ability to capture light from galaxies formed just 300 million years after the Big Bang, JWST is providing insight into the initial stages of galaxy formation. The presence of massive, mature galaxies at such an early stage of the universe challenges the conventional theory that galaxies should have taken longer to form. This raises the possibility that some processes, such as star formation or black hole growth, may have been far more efficient in the early universe than we thought. Furthermore, these unexpected findings have implications not only for galaxy formation, but also for understanding the role of dark matter in shaping the universe's structure. Dark matter is believed to have played a crucial role in the formation of galaxies by exerting gravitational forces, yet its exact nature remains a mystery. JWST observations could help illuminate how dark matter influenced galaxy formation, potentially revealing new properties of this elusive substance. In addition to dark matter, JWST is also advancing the study of exoplanets and the conditions necessary for life beyond Earth. One of the telescope's primary missions is to analyze the atmospheres of distant exoplanets, searching for signs that could indicate habitability or even life. By studying the chemical makeup of exoplanetary atmospheres, scientists hope to uncover the conditions under which life might arise elsewhere in the universe. These findings could offer valuable insights into whether Earth-like conditions are rare or common in the universe. As we delve deeper into the data from JWST, it is becoming increasingly clear that we are on the brink of discovering new physics. Whether it's the evolving nature of dark energy, the surprising complexity of early galaxies, or the elusive behavior of dark matter, JWST is opening up new avenues for understanding the universe. It is not only refining our current theories but also challenging them, forcing scientists to think in new ways and consider the possibility that some of our most fundamental assumptions may need to be revised. Moreover, These discoveries are advancing our knowledge of cosmology while also pushing the boundaries of particle physics, astronomy, and even philosophy. As we continue to explore the universe through the lens of JWST, we are not just learning about stars and galaxies. We are gaining a deeper understanding of the very laws of physics that govern our existence. The questions raised by JWST's findings could lead to a paradigm shift in our understanding of the universe's origin.